Hello, everyone. Thank you for taking the time to join this MeshWorks webinar series to enhance the efficiency of the analysis using reduced order models. So myself, I'm Gautaman. Along with me, I have my colleagues Sai and Rajat joining and walking you over some of the slides as well as live demos for this webinar. Jumping directly into the webinar. So first of all, who are we? We are DEP. DEP stands for Detroit Engineered Products, founded in 1998. So we have four different verticals: the consultancy services vertical, the software development, and that is part of the MeshWorks platform, the product development, and the talent acquisition. As a part of the organization, we have the research and development activities in-house as well as globally. We are headquartered in Troy, Michigan, with offices in various geographies like India and China. And the other regions, we are supported by our distributors in France, Italy, and so on. So this is the overall team. So we have about directly 550 plus engineers, and you can see the direct offices marked in red color and our distributors marked in blue color. And this is just a partial list of our customer base who've been using the different business verticals of DEP. And our journey so far. So, like I mentioned earlier, we have our headquarters in Troy, Michigan, founded in 1990. And we started our operations in India in 2000, and we launched the first version of MeshWorks in 2001. And then every other alternate year, we had significant developments like opening new offices, opening new product development activities, opening up labs, and so on. And in the current years, we have opened up our fourth office in India, in Tirunelveli. And this year, we actually launched an in-house battery simulation methods lab. With that said, let's quickly jump into today's highlight, which is MeshWorks. So MeshWorks is a CAE platform. As you can see, these are all the different types of modules inside MeshWorks. As some of you are aware of, MeshWorks has been predominantly into CAE morphing, parameterization, enabling you to do multidisciplinary optimization. But we are also into preprocessing as well as post-processing. When I talk about preprocessing, it includes all the types of meshing, starting with a dead mesh, shell mesh, mid-plane mesh, and all the types of connections with 1D bolt connection to all the way through the welds, seams, adhesives, etc. We also support different modules of post-processing like Nastran, Abacus, LS-DYNA, and so on. And with that being said, with the pre and the post processor, we understand there's going to be a lot of customization options that the customer is looking for. So we also have our highly automated process automation environment where you as an user can create these customized tools. And we have a groundbreaking concept modeling tool where if you have a data to start with, yes, we can do all the sorts of morphing and parameterization. But if you do not have a data to start with and you want to create new bill of materials, that's where the concept modeling comes into the picture. And we have new modules, which is the innovative ROM module and the product electrification module. So today we are going to do a deep dive into the ROM module. We are going to see some very cool demos as well. And one thing I want to set up the stage is the MeshWorks applications at different stages of your product development lifecycle. So this is a very cool graph that we see here, which nicely gives you what is the current trend versus the new trend. The current trend is to push the CAE as much as possible in the detail phase. That is where once you get the CAD data, we do the meshing, modeling, connections, do the analysis and subsequent design iterations. And again, going back to the CAD data. But in the latest stage of the scenarios, what we see is the CAE is pushed into the conceptual stage itself. That is, we do a lot of design iterations in the conceptual stage without the help of CAD data, and CAE is now driving the designs without the help of CAD. So when we look at the conceptual stage, MeshWorks really helps you in a lot of ways where you can do morphing, parameterization, do rapid design changes like the cut and stitch methodologies, and all that stuff where without the help of CAD data, we can do. And then when it comes to the detailed stage where you have a CAD data, all the steps from meshing, modeling, connections, everything can be again done inside MeshWorks. So when it comes to the validation phase or the maintenance phase where you want to do some manufacturing robustness analysis, again, our MeshWorks can help you in all these kinds of product development life cycles. And coming into the innovative ROM module, ROM stands for reduced order model. So the entire idea is to convert the detailed model or a 3D model into a representation of 1D BOM models. So in the case of Nastran or Avacus, it could be a representation of beams, bars, and so on. In the case of LS Dyna, it could be mass inertia representations. So we are going to do a deep dive into all these kinds of different setups. But this is going to give you a gist of how cool and innovative the ROM module is. So what you see here is the styling theme. And from the styling theme, if you usually the CAD team or the architecture team gets the critical cross sections. So we can very quickly validate whether these critical cross sections are really meeting all the performance characteristics. So these cross sections are used to create the 2D models or the detailed model, and we have very good scripts wherein in the detailed model we can apply different kinds of load cases. And if it is not meeting your performance criteria, quickly parameterize the models at the 1D level itself, at the section data itself. And once you do the parameterization, again, drive the detailed model. So whatever we are talking about is just like a B pillar and A pillar kind of scenario. In the subsequent slides, we will also walk you through the entire body in white. And once you drive into your optimized design, then you can get the detailed FE model, and from there we can drive the CAD design. So this way, your analysis time is very much reduced because we are completely working on a section data. Coming into the next example here, which is the raw model for a full body in white. So the conversion of a 3D model to 1D model, do the optimization, get the optimized sections right, and then convert these optimized sections back to the 3D model. So this, all the three steps can be handled very quickly and very easily inside our ROM module. And since the detailed model is now converted as a part of beams representation, the time taken to run the model is also very quick. And once the optimization is completed to convert the 1D model into 3D model, we use our concept modeling tools to create the detailed body in white. So this is an example of how we are representing the body in white using just the beam model. So the beam models, whatever the sections that you see on the screen are just a representation of the beam properties. And I am just going to quickly play a video of how easy it is to create the Nastran ROM model or an LS Dyna ROM model, which we are in turn going to take a deep dive into the demos. And coming into the correlation studies, so you can see that we have done the correlation for both the Nastran as well as LS Dyna, and we see a very close correlation between a detailed model as well as the ROM model. and the time taken for the ROM model to run is just under 5 minutes, and you'll be getting the results that much faster. And depending upon the template, you can see somewhere between reduction of 50% to even more than 80% reduction in the case of Nastran. And with that being the stage, I'm going to pass over the controls to Rajat, and he's going to show you some of the cool demos of creating a ROM and a Nastran model and how easy it is. Over to you, Rajat. I'm going to stop sharing.
Hi, everyone. I hope you're able to see my screen.
Yeah, we're able to see the screen.
Sure. Okay. So first we'll start with the creation of ROM for the Nastran model. So I have this BIW model of a car, and we are going to convert this BIW model into a ROM model, a reduced order model, which is like a 1D representation of the original model. So this will help in reducing the runtime for the model. So I'll straight up proceed with the demo. So we'll go to modeling, and we have the ROM capability. So we'll go with the ROM Nastran. And first, the first step is to create blocks. So I'll start with the block creation. So for creating blocks, all we have to do is pick up the nodes on both of the sides of the B pillar. So I'm going to create a block here around the B pillar. So I'm picking up nodes. And then the nodes at the other end. And then we can provide an appropriate mesh size and the block size. And then say create block. So it has created a block here. It will create a block and a 1D CAD and a CAD curve around the block, inside the block. We also have the option to adjust the block. I'm going to quickly show you that. So before proceeding, we have to ensure that the block covers the entire section. So you can see some amount of some amount of the section is protruding out of the block. So it's supposed to cover the entire section, but we have tools to do quick adjustments. So I'm going to click on the component and the elements, and then do a quick adjustment. As you see, now it's fully covering the section. So you can quickly adjust the blocks using this tool. We also have the option to reflect the block. So all we have to do is select the control block and the CAD curve. And just say reflect. It will automatically reflect the block to the other region. And again, we can make sure that the block is covering this region by doing a block adjustment. So the first step is to create these blocks. The next step would be to create the beams. So in the interest of time, I have already created 5 blocks, and here I'm going to show you how we can quickly create beams using the ROM tool. So again, we have to go to modeling, ROM, and modeling for Nastra and Abacus. And here we have the option of create beam. So the first step is to pair the control blocks with the CAD curves. So for the ease of selection, I'm just going to hide the 2D and have the blocks in the wireframe. So I'm going to select this block, then the CAD curve, and say pair. And I'm going to specify the number of sections here to 5. So what it will do is it will compulsorily create two sections, two 1D representations of the sections at the start point and the end point, and 5 more sections between the starting and the ending point. So it's going to create a total of 7 1D sections, which would represent this B pillar. And similarly, I'm going to do the same steps for the other 4 blocks. Yeah. So since this is a bigger section, I'm going to give more number of sections. Going to selecting the block, selecting the CAD curve, and as this is a smaller one, I'm just going to go with the 2 sections. There. So this way, by specifying the number of sections, we have the control over how many sections we want for any particular part. If it's a bigger one, we can give more number of sections. So I'm going to specify a path for the CSV file generation. And the path for the working directory. And as it's a closed section, I'll go with closed section and just say create beam. So immediately it will start creating a beam, and you can even the text file over here. So it has started creating the beams. This process would take around 5 to 10 minutes. So in the interest of time, I'm directly going to show you the final beam model. So this is how it would look like once the beam creation is done. You can see all this, the entire BIW section, the 2D elements have been deleted, and instead 1D representations have been created. And you can see we have a total of over 7 sections around here. So in this way, we can convert by giving minimal inputs. We can convert a section into a 1D beams. So next, I'm going to proceed with the joint creation. So we already converted the sections into beams, and now I'm going to show how we can create joints using our ROM tool. So we can for this, in this case, I'm going to show this particular region where we have 4 sections, and we need to create a joint between these 4 sections here. So I'm going to go to the ROM tool, and first we'll go with the joint node creation, and I'm going to go with the bit node creation. and simply select 2 nodes. Let's say create. So it has created a point in between. We even have the option to do the node adjustment. We can simply select the node and specify a vector or a direction and distance and modify this point. So next I'll go with the beam joint modeling and select 2 opposing rigids as set 1 and these 2 opposing rigids as set 2. This is set 1 and this is set 2. And then select the center node. And then I'll we can specify the element size for the 1Ds and say create beam joint. So just by giving the rigids as the input and the center node as the input, we can create a beam joint using this tool. This would take about half a minute to a minute for execution. Yeah, so it has created a beam joint. Using this, oh, I think by mistake I selected another node because of the zooming. If I had zoomed in and selected this node, it would have created the point over here. Yeah. So next I'm going to show parameterization and how easy it is to parameterize these sections for DOE and optimizations. So we have a model over here. Just going to hide the shells. So we already have, I've already created some parameters, but I'm going to create more. And I'm going to show how we can quickly create parameters using our ROM tool. So here we have to go to reduced order modeling, control block parameterization. All we have to do is select the 1D components. And select the 2 nodes along the width direction and say preview block. Should take about half a minute. Yeah, it has created a control block. So using this control block, it will create a parameters. We can create parameters. And again, all we have to do is provide the minimum and the maximum height and the width, and just click on create parameters. It has created the parameters. You can go and review it. So these are the parameters that we have created previously, just for just to showcase for this webinar. So it has created a total of 4 parameters. You can see it's already highlighting the control nodes. And the first parameter is for height change at the bottom. You can see this region. Second one is again for height change for the top section. I'll put this in wireframe so you can get a better idea. So this is for height, and similarly it will you can create for width change as well on the left and the right section. And on the right section, the width change on the right section. So similarly, we have created, I'm just going to review a few parameters and proceed with the next demos. So similarly, we have created parameters for different regions. Can just review a few of them, but it's a similar parameters. For example, on this section, so and these are again it's a similar parameter. The height change on the top, the height change on the bottom, the width change on the left and the right side. Should hide these digits. Yeah. So in a similar way, we can quickly parameterize even the 1D ROM, the 1D beam models that we have created, and we can do quick cross-section changes using this tool. So for the next demo, I'm going to show crash load case PA. So we have a special tool where we can create a special tool and a PA for creating crash load cases. So I'll go with crash load case setup. This is our special tool, and I'll go with model settings. First, I'll import the Dyna file. And then we can specify the comment card that we want. We have HM, ANSA, or primer for the load case setup. And again, we can set up load cases for different situations like full frontal crash or side impact or a mobile deformable barrier and so on. So in this case, I'm going to go with mobile deformable barrier, MDB side load case. Next, I'll specify a file path for exporting files, and simply say load model. And then we can specify the template here as Dyna, and it has loaded the file, the Dyna file. So we just have to give minimum inputs, and it will automatically, this tool will generate a MDB side load case model. So here we have to give the first input that we have to give is the vehicle driving direction. So the vehicle will drive in this particular direction, in the positive X direction. So I specified positive X, and then we have to give some basic geometry inputs, and the location of the left front wheel. Just select one node here, and left right wheel. selecting another node here, and that's it. Then we just have to click on save data. The settings are saved. Click on return, and all you have to do is select the components and say create bounding box. So it will create about within a minute or so, it will create a bounding box around this car, around this model. Yeah, it has created a bounding box which is represented by this control block, and then all we have to do is give the front face, the bottom face, and the left face as the input, and say create load case. Again, it would take about a minute or so to generate the load case file. So it's generating a Dyna file which would have that particular load case, the car and the MDB side model with it. It says load case created. So we go to the folder. It has just now created the Dyna file with the load case setup. I'm just going to load the file and show it to you all. The input. So importing that particular model. So you can see it has created a MDB side load case model here. So just by giving minimum inputs like the driver wheel direction, the positions of the left and the right wheel, and creating a bounding box, we can quickly create a MDB side load case using this particular PA. So that's it from my side. So I'll hand it over to Sai for the next set of demos.
Thank you, Rajat, for the wonderful demo. I'll quickly share my screen. Is my screen visible?
Yes, Sai, your screen is visible.
Yeah. Hello, everyone. Thanks for joining. So today I'll be demonstrating some of the crash cases and how we can create raw models on these for crash load case setup. So here you see on the screen is a full vehicle model. Now what I'll be doing is I'll be creating a ROM model out of this full vehicle model and see how we can do that in using MeshWorks. So here in the modeling module, we have this ROM panel. So here we have various cases for ROM, Nastran, Abacus, LS-DYNA, depending on whatever load cases you want to solve for. I'll go with the reduced order modeling LS-DYNA. So in this we have three sections which are needed for this ROM creation on this model. First is a block creation. I'll go to create block. So I'll put this in a view. Now what I want to do is I would like to create the rear portion of this vehicle into a ROM model. So we'll go to create polygons and now we'll start sketching the blocks. Let me put this into, turn this off. So we want to make sure the entire FE model of this vehicle is enclosed within these blocks, so that it is easier to convert the entire model into a ROM model. We'll bring that on. Okay. I'll click on accept. We'll give the layer count as 3, and I'll go with default inputs. And when you hit on extrude, it will create blocks, as you can see. So the entire vehicle is enclosed within this blocks, and I'll click on accept, return. And now the second step is to create mass elements. So whatever the FE elements within the second half of the vehicle, which are enclosed within this box, will be created into a mass elements, 0D elements. So I'll select this as elements, and when you hit on create mass, it will go ahead and convert all of these elements enclosed within these blocks into a 0D elements. It will take about 5 minutes. So in the interest of time, I'll pull up the already converted model. So here, as you can see, the second half of the vehicle is entirely converted into a ROM model. So this is what the mass conversion output looks like. Now I'll append the suspension, rear suspension. As you can see, I've appended the rear suspension. Now we would like to make connection between the FE model as well as the ROM model here. So for that, same going into the ROM module. Here in the third section, we have create rigids. So this is where we'll create connection between both of these elements. So that connection can be made as a single nodal connectivity from each node to this FE vehicle, or we can also do as a multiple node connections all at one shot. So I'll go with the multi-node connection. So I'll select all these nodes on the 0D elements and all the nodes on the 2D elements on the left side. The entire cross section has been covered. Now when I click on create, it will create a connectivity between the front of the vehicle and the rear of the vehicle. So in the similar fashion, we can create the rigids between 0D elements as well as the suspension system. So which I've created, which I'll quickly show you. So this is the model, with the connections that has been established with the suspension systems. As you can see, at each points, we have established a connection with the front of the vehicle as well as at the suspension system. So this is how easily we can create a ROM model for crash load case using MeshWorks. So these ROM models basically, reduce simulation runtime as compared to full vehicle models. Now that you have seen ROM creation on a full vehicle level for crash purposes, now Gautaman would be showing ROM setup for subsystem levels. With that, over to you, Gautaman.
Thanks, Sai. So let me go ahead and share my screen back. Okay, so coming to the demo. Like Sai mentioned, we saw how easy it was to convert a rear portion. Since we are looking at a frontal crash and the intrusion is all going to happen only on the front side of the vehicle, we want to convert the rear portion of the model into mass inertia representation. Similarly, when you want to work on some subsystems and you are not going to really worry about the actual component being there, but in case the mass representation is going to be good enough for analysis, we can go ahead and do that. So right now you can see that this is a complete battery cell module, and I have some views where we have all the battery packs. So in this case, we can go into the ROM module, the lumped mass creation. It supports both LSDNA as well as Nastran. Here I'm going to select a bunch of elements which represents one module. And then I'm going to choose what type of connection it needs to be. Whether here I'm going to choose that once converting into a mass inertia representation, go ahead and connect them through rigids by using the mounting locations. And I don't have a specific node, automatically the tool is going to find that out. And then I'm going to specify what is a connection type. Either it can be a nodal rigid constraint or constraint interpolation type. And we also want to delete the elements that we selected so that the tool calculates the mass of this particular module, creates a mass and inertia element in the centroid, and then connects them to the surrounding components with the help of this nodal rigid body. So give it a second. Yep. So now you can see that it automatically finds the connecting regions and establishes the connection. And you can also see that in the center, we have the mass representation. Let me go ahead and switch off the 1D for a second and switch on the handles. So you can see that the mass and the inertia are represented in the point. So this is how easy if you want to quickly convert a subsystem or any sort of assembly as a reduced. And with that, let me go back to the presentation. And we can see that we have gone through all these demos focusing onto ROM crash as well as ROM Nastran. Now let's talk about the model where we convert the detailed model into a reduced order model. So here you can see that the input model from a detailed model to a ROM model is having about a 30% reduction on average. So there is a good amount of node and element count reduction, which essentially gives a lot of efficiency while running the model. And how about the correlation? So let's take a look at the correlation. So this is one of the load cases which we have run the model for, which we are sharing. And this is the crash ODP LH load case. On the top, you can see on the top LHS, you can see the detailed model, and on the right hand side, you can see the reduced order model. This is on the animation side. Now let's take a closer look on what is happening when it comes to the baseline intrusions, all the different types of intrusions, versus the detailed model intrusion. As you can see, the model takes about 50% lesser time to run, and the results that you're seeing on the screen is also having a high degree of correlation. So which means that if you look at it, there is a difference between, depending upon the measuring points, there is about 80% to even 90-95% correlations with respect to the detailed model. And not only that, if you want to do any sort of parametric studies, let's say on a full frontal crash, you want to set up some parameters on the crash can, parameters on the sill, shortcut region, all these parameters like shape parameters, beats, bulkheads can be created on the ROM model. And this subsequently also runs very fast for your design iterations. So just to conclude on the topic, MeshWorks is a professional grade C pre and a post processor, and we are able to generate multiple designs using a single design file, and this will enable you to do all the optimizations. And MeshWorks transforms your product development lifecycle through tools like morphing, concept modeling, process automation environment. Since we have the process automation environment, it gives you the flexibility to customize functions so that whomever is going to use the tool, from even a novice engineer to an experienced engineer, they are going to see similar kind of results. And it's using all these tools like ROM, the battery tools, you can accelerate your product development life cycle, and the innovative modules are also going to help you significantly in your workflows. So with that being said, I'd like to conclude today's session on this particular webinar on ROM.
So attendees can write to email at dpusa.com or webinars at dpusa.com if you have any queries.
Thanks everyone for joining this session. Thank you.